Okay, so here's where we're covering chapter 2 on voltage and current. So this is chapter 2 in your Robbins and Miller book. It's chapter 2 in your Boylestad book as well. You'll see it carries the same title for both books. At the end of this chapter, just look under the content section on our Brightspace or D2L page, and you'll find the practice questions based on which book you have. So yeah, that'll be what we do when we're done here, is do the practice questions. All right. So I wanted to start with this water system comparison for understanding these electrical quantities. So it's a very common analogy to use water, something that we can probably all relate to in terms of using a water system in your home or your place where you live. And being that water is a visible thing, we can relate to it because we've seen it. Whereas electricity is invisible, so it's harder to be able to see. Of course, how does electricity do work? Well, much like water in a pipe, electricity performs work through the moving mass of electrons moving in a circuit, and because they're so small that we can't see them, it's hard to relate to. But if we think of electrons like water flowing through a pipe, a lot of times it helps us as beginners to understand the properties and physics behind it all. So in this example, notice how I've got a pump here, a pump on the left hand side, and when the pump is running, that is, there's some type of input or energy input to create this, or to move this pump. On one side, the lower side here, we have a low pressure created, right? So this is suction, low pressure. On the other side, we have high pressure. So we've created a potential difference or a pressure difference by the pump. So we could say we have a positive pressure over here, a negative pressure there. The negative pressure or low pressure causes suction to the pump, and the positive pressure causes the pump to be providing flow. So we would say there's flow through this pipe. And remember, this pipe is a conduit for the movement of water. It holds water in and has no holes in it, such that it contains the water within this conduit or this water conductor called a pipe. And we'll be able to relate this all to electricity as we go forward. So notice how here we have a restriction in the pipe. So what would be the result of the restriction? Somebody stepping on that hose or squeezing that pipe to lower its diameter. Well, we would end up with a high pressure on one side and a low pressure on the other, and this would result in work being done, and there would be work required, or there'd be work produced by the flow being pushed through that restriction. So one thing to note right away here is, notice how with the pump there's a pressure difference or a pressure differential, and it will always be there even if you were to stop flow entirely with a valve in here or a shut-off valve to turn it off. That pressure would remain. So there would be source or pump pressure without flow. Notice over here, for the restriction is dependent on flow. So the restriction would be dependent on flow to create that pressure differential. If that restriction was there, yet there was no flow, there'd be no pressure difference, as you can imagine. If there was a valve in here turning off flow, you would see a high and low pressure from the pump, but you would not see a high and low pressure from the restriction, because the restriction is dependent on the flow. So that's something we can draw right away from this system, is that a difference or potential can occur from a source or a pump, but it's not going to show up from the, no work is going to be done, or no pressure difference is going to be present when you have a restriction without flow. So we could say that the pressure difference for the restriction is dependent on flow. The source or the pump is not. One other thing I'd like to point out is, let's say you were to look at the pressure difference in this whole area of this water system. It would be high pressure during that whole, in that whole section of pipe. That would be high pressure. So what would be the difference in pressure from, say, point A here to point B? You've got the difference between high pressure and high pressure. That would be zero pressure differential, right? But look, if you were to take this point as point A and this point as point B, point A would be high pressure, point B would be low pressure. There would be a difference of potential that's equal to the high pressure and the low pressure difference. So this is all how we can relate to electricity in terms of these quantities. Electricity operates the same way. It's just that it's not water flowing through these pipes, it's electrons flowing through wires or conductors. Okay, so that's just kind of the initial start to our understanding of an electrical system and the energy being transferred from the source to the load through the use of conductors and the flow of electrons as opposed to water. Okay, so where we started all this, because it has to do with electrons and the fact that it's electrons that are like our moving mass of water in our water system. We start by just reviewing what we know about atomic theory, and therefore we can classify materials and things that we use in electric circuits into one of three categories. So an atom consists of a nucleus of protons and neutrons surrounded by a group of orbiting electrons. And these are really the ones that can be freed from an atom and used to do work, which we call electricity. So electrons are negative, protons are positive. And of course, in its normal state, we know we have an equal number of electrons and protons. So if we look at this probably common orbiting system that involves the nucleus of the atom in here, where you find all your protons and your neutrons, you have orbiting electrons. Now the thing is, depending on the type of material, there can be several orbits or just a few. So what's most important to understand is that when we have these orbiting electrons, the outermost orbit is the one that determines its electric quantities, right? So when we have an electron in the outermost orbit, the farthest away from the nucleus, this is what's called a valence electron, because it's in the outermost shell or orbit called the valence shell. So the outermost shell of an atom is called the valence shell, and the electrons in this shell are called valence electrons. Makes sense, right? Outermost shell is called the valence shell, so the electrons in it are called valence electrons. Now, here's the important part. No element can have more than 8 valence electrons. You won't find any material with more than 8 valence electrons. It can have less than 8, but it won't have more than 8. The number of valence electrons are what determines its electrical properties. And here's the last part. Fewer electrons means better conductivity. So it means that any of your common conductors like copper, aluminum, silver, gold, those are all materials that have very few valence electrons. So if we take a look here, we can see that we have atom who has 29 protons, 29 neutrons, and this is actually going to determine where it appears on the periodic table. Whatever this material is, it's number 29 on the periodic table, indicating it has 29 protons and neutrons, and therefore, of course, 29 electrons as well. So if we look at the outermost orbit here, though, notice how in this case there's only one. Yeah, there's only one valence electron in the outermost orbit, and that's called its valence electron. So conductors are the ones that have from 1 to 3 valence electrons, where 1 is the better conductor of what we see here, and 3 is the least good conductor of a material that's 1 to 3. But the understanding is that when we have 1, 2, or 3 valence electrons, this is classified as a conductor. So metals are generally good conductors because they have few loosely bound valence electrons. Silver, gold, copper, and aluminum are all excellent conductors. I often ask my students in face-to-face class right now, out of this list, do they know which is actually the best conductor in that list? And they'll often pick gold because somebody's told them that that's a superconductor and it's the best conductor you'll ever find. Well, it may be the most valuable metal in all of that list, but it's actually silver that you're going to find is the best conductor out of this list here. And in our everyday wiring, we commonly use copper, but there's other properties for copper that make it the most practical conductor, and that has to do with balancing cost against the flexibility to be bent in a wire and its corrosive or non-corrosive properties. So copper is very common in aluminum, but if we were to just be looking for the best conductor in that list, the answer would be silver. So then what are we looking at when we look at the other end of the scale? Well, we're talking about a maximum of 8 electrons. If we work our way back and develop another range at the upper end, we would have 5 to 8 valence electrons. So when we have 5 to 8 valence electrons, that's classified as an insulator. So these are materials that do not conduct and are full or almost full of valence electrons. So glass, porcelain, plastic, rubber are all good insulators. So we use all of these in electric circuits to prevent electricity from flowing. Because I think it's important to point out that, you know, a practical electrical circuit's not just looking to use conductors to create its circuit. There's times where we need to bring in insulator materials to prevent electricity from conducting. So as an example, the insulation around a wire so it doesn't short out to other conductive surfaces. To insulate in power lines so the power lines don't short out with the supporting structures and things like that. So, you know, we don't just exclusively use conductors in electricity. We use insulators to house conductors so that they will conduct like pipes, water or electrons to go where we want them to go, to direct them to the work producing load. Now, here's an important statement that kind of summarizes all this. If high enough voltage is applied, an insulator will break down and conduct. So what it means is when it comes to these materials, even though these are classifications, you can still find that a material with 5, 6, 7, or 8 valence electrons will allow electrons to flow. And it'll happen if the voltage is high enough. So the example is lightning, right? When we think of lightning and millions of volts, that can cause things like trees and other things that are not conductive material to conduct electricity to ground. And so that's important to know, is that even though these are classifications, if the voltage is high enough, you can get any material to conduct. And so when we're looking back at this, we, you know, think of the water analogy, right? If the pressure from that pump was high enough, it would actually burst that pipe, right? And it would mean that the essentially insulating material on the outside broke down, and water was allowed to flow external to the pipe. So the insulation broke down because of why? The pressure was high enough, or the voltage was high enough. Okay, so when it comes to the very middle of this scale, you can kind of think of the 1 to 3 being conductor, the 5 to 8 being an insulator, but right in the middle then it means we have the 4 valence electrons. And a 4 valence electrons is a special material called a semiconductor. So semiconductors are half-filled valence shells and are neither good insulators nor good conductors. Examples are silicon and germanium, and these are used to create transistors, ICs, or integrated circuits, diodes, and all the kind of devices you'll be looking at in the second half of your electronics course. But what makes those special is that by applying voltage, you can either tip them to be a conductor or to tip them to be an insulator. And so that means you can either have them being fully conductive like a short circuit or fully non-conductive like an open circuit. And of course this is what's actually describing an electric switch. So semiconductors are often called solid state switches. There's no actual moving contacts within them, but by the use of external voltage you can have them act like a conductor or an insulator. So they can go from a open switch and allow no current flow to a closed switch and allow current. So that's what makes the semiconductor a really special material that we use in electricity. So how do we actually describe electric charge? Objects become charged when they have an excess or deficiency of electrons. So remember, an electron is a negatively charged particle, or a negatively charged object, if you want to think of it that way. So if that's the case, if we have an excess of them, we would have an excess negative charge. Okay, what about if we were deficient then? If we were deficient of electrons, that means essentially the protons would take over and be the majority, and that would give us a positive charge. But the thing is, it's only the electrons that can be removed, or you can either only have an excess or a deficiency of electrons. So when it comes to a positive charge, that's not described by extra protons, it's described by a deficiency of electrons. When they're gone, it leaves positive charge behind. So now, what's our unit or SI unit for electric charge? It's something we call the coulomb. Okay, so 1 coulomb is equal to 6.24 times 10 to the 18th electrons. That's a whole lot of electrons, of course. And of course, because electrons are so small, it takes a whole lot of them to do any real measurable work. So 1 coulomb is this many electrons. Now, you're never going to be asked to remember that, don't worry. But it is defining specifically the amount of charge for a coulomb. So voltage then. Voltage is equal to the pressure in our water analogy, right? So if you're ever trying to sort of understand what's voltage, what's current, voltage is equal to the pressure. And remember, we talked about how there can be a potential difference, or what we're now going to call voltage, from a source, but it's only going to be present on a load when there's flow. So do you remember in the lab when we looked at the variable DC power supply? We could measure a pressure difference. I'm going to use that term for now. We could measure a pressure difference with the voltmeter. We could see that one side had a negative charge when compared to the other side as a positive charge. There was a potential difference, or a voltage or a pressure difference between them. This is something that we in electricity called voltage, and the unit of voltage is, no surprise, the volt. Now, a difference in electrical potential energy is defined as voltage. The voltage between 2 points is 1 volt if it requires 1 joule. Now, a joule is our SI unit for work. If it requires 1 joule of work to move 1 coulomb, so 6.24 times 10 to the 18 electrons, of charge from one point to another. So, voltage equals work divided by charge. Joule divided by coulomb. Work divided by charge. Now notice how, and this is important, voltage is always defined between 2 points. In order to have the difference, you have to have 2 points. With a single point, there can be no difference. With 2 points, this is when you can find a difference. And notice how, if we go back to the water analogy I used the idea of, if you were to look at any point on that circuit, the only way you're going to find a difference in pressure is to be on either side of the pump or on either side of that restriction. If we were on the same side, we would have an equal pressure. So we'd be looking at 2 points without a difference. And so there would be no voltage other than across the pump or across the restriction. So voltage is defined between 2 points, always 2 points. Notice how I used the points A and B in the example when I started. So how about current then? Well, current is the movement of charge and is called electric current. The more electrons that pass through a circuit at a given point, the greater the current. So current is the rate of flow. And so if you think about that water circuit, based on the pipes and the pump and the pressure, that's going to determine the flow of water. And if we had more pressure, there'd be more flow. So when it comes to current, current is dependent upon that pressure. Current is dependent on that voltage to determine how much current there will be. And the thing to realize here when you're comparing current to voltage is current is defined by a single point of measurement, whereas voltage is the difference between 2 points. So when we're talking about a single point of measurement, if we think about, say, that water flowing through that pipe, right? So we've got water flow here. The way we would determine the flow is to determine what's the volume of water passing by a single point A. So if I saw 2 gallons go by that single point, so a volume of water of 2 gallons go by that single point in 1 minute, then I would have a flow rate of 2 gallons per minute. So it's defined as a rate. Remember, rate is always a quantity versus time. And here's what we have, 2 gallons per minute. That would be my flow rate. So the unit of current is something called the ampere. So we had volts for voltage. Here we have something called ampere. And it's symbolized by uppercase A and often just called the amp. Often just called the amp. So 1 ampere is the current in a circuit when 1 coulomb of charge passes a given point in 1 second. So notice that's a given point. That's a single point measurement, right? And how much is 1 coulomb? Well, 6.24 times 10 to the 18th electrons, right? So notice how here, in order to demonstrate current and the electrons flowing in this circuit, notice how we've taken a single point, or essentially a divider or plane, and basically counting the number of electrons passing by that single point in 1 unit of time, right? And it would be those that are determining our flow. It would be the electrons that are passing that point determining our flow. And our current then would be defined as charge per unit time, or Q standing for coulombs per unit time, as minutes, hours, seconds. Okay, our SI unit for time being seconds, of course. And this is I, corresponding to current. So I is current here. Okay. Here you see the schematic symbol for a battery. So this is a DC source. Notice how you have a load here. So this is the component doing the work, right? And so this is the work producing lamp that, as a result of flow, causes light to be emitted from that filament, from that bulb. But along here is where we'd have all of our low pressure, if you want to think of it that way. This would be all low pressure. This would be all high pressure. And now, across the lamp, we would have a difference of pressure from there to there. And across the source, we'd have a difference of pressure. Positive pressure here, negative pressure there. If we assume current flows from the positive terminal of a battery, we say this is conventional current flow. Now, the thing to understand is that when we're talking about standard electric circuit and connecting, say, a battery as a DC source, and current starts to flow, the actual work being done is from the movement of electrons, and those are leaving a positive terminal and being attracted to a negative terminal. We think of that as opposites attract, like charges repel each other. So there is no doubt and no argument that the direction of electron flow in a circuit is from negative to positive. And some curriculum shows current flow in all of its demonstrations as exactly that, negative to positive. But when it comes to our course and SAIT's electrical standard for current flow direction, they use what's called conventional current, what we see here. And then that means it flows positive to negative. So all of our examples will show positive to negative. And what it's just simply illustrating is the flow of positive charge as opposed to the flow of negative charge. And it really doesn't matter which direction you think of current to be flowing for analysis. You can think of it as the flow of positive or negative. It doesn't matter. It still has the same ability to do work. The calculations are all the same, and everything is consistent from one to the other. It's just that before you start any curriculum, you really need to know whether you're working with conventional current flow or electron flow, so that you have a consistency between the way you're communicating current and showing current and so on. So hopefully that makes some sense. So just once again, conventional current is used in this course, and all of SAIT actually uses conventional current in its trades, electricity, and in engineering. So in lab we mentioned this. Remember, DC is current that's always in one direction, and that comes from a source with fixed polarity, right? So if I show the schematic symbol for a battery here, this is the positive terminal with the larger plate. The smaller plate is the negative terminal. So because there's fixed polarity, this one is always positive and this one is always negative, then this is called a DC source, and it causes current to always be in one direction. Now, if we take something like an AC source, which schematic symbol looks like this, what we have is a source that is constantly changing amplitude and polarity. So it may start at time 0 with this polarity, but then by the time it goes through its full cycle, that polarity changes to a minus plus. So it's over time that it changes both magnitude or value and polarity, right? So if we look at a 0 volt value here over time for DC, let's say this was 12 volts, we would have 12 volts positive with respect to 0 volts over time. So time would have a steady 12 volts. If we were to look at this guy over here and look at 0 volts, and we were to look at time here, we would have the first half of the signal would be positive and the other half would be negative. So over time we'd have positive and then negative with respect to 0 volts. That describes a AC source, alternating current, or AC, and the current in an AC circuit, like in your home or your all the buildings at SAIT, it changes direction cyclically. So every time we switch polarity in this signal, the current changes direction. So it's going back and forth, back and forth. So just to look back at this current, this will be the SAIT standard, and this will be the way your textbook is. It'll, whether it's Boylstat or Robinson Miller, it'll be showing the direction of current in this direction, leaving the positive terminal and returning to the negative terminal. And this is really looking at the flow of positive charge. This is called conventional current. If we look here for electron flow, that's an electron leaving a negative terminal, being repelled by the negative charge and returning to the positive charge. This is the flow of negative charge, which we know as electrons. Right? Now, again, in this course, we don't use this. All of our curriculum shows conventional current. So this is something we did talk a little bit about in the lab, and that is even small amounts of current through the human body can cause serious and dangerous side effects. Any current over 10 milliamps is considered dangerous, and I told you that at 10 milliamps you can just start to feel it. Currents of 50 milliamps can cause you to feel like you've really got a shock, and then currents over 100 milliamps, as I mentioned in the lab, can often be fatal and can kill you. So just a last line here: treat electricity with respect, but you don't need to fear it. And we mentioned how come, even though our power supply in the lab is capable of 3 amps, why do we not need to be fearful of that 3 amp power supply? And it's because of the voltage is not high enough to ever cause 100 milliamps of current through your body. And so you don't need to feel threatened by that 3 amp power supply, because the voltage is low enough, because we have a low voltage. So if we're looking at voltage sources now, batteries are an example of a DC voltage source, and they're probably the most common DC power supply you're going to find is a battery. Batteries are in everything, right? But of course there is other examples of DC sources like solar cells and thermocouples and things like that. But for now we're just going to concentrate on the battery. Now, when it comes to a DC source of any type, one terminal is always positive with respect to the other terminal, and likewise, the one terminal is always negative with respect to the positive, or with respect to the other terminal, which would be the positive. So we have this fixed polarity that, when connected to a circuit, will always cause a direct current, or a fixed direction for the current. And in our case, what direction would we consider that to be for our purposes of our analysis? It would be from plus to minus, conventional current. So battery technology is constantly changing, and this slide taken from your textbook is really kind of indicating how maybe old, if you want to say, or outdated your textbook is, because the list of chemical makeup for batteries can go on and on here, much greater than what we see here. And one of the biggest breakthroughs in batteries, as of late, over the last maybe decade or 20 years, has been lithium ion and lithium polymer. And it's the LiPo, or the lithium polymer battery, that has allowed huge maximum currents, large capacities. So when I say capacities, able to store a lot of charge to be delivered to a load, but also provide maximum current, and to have low weights, so they don't weigh very much. And so because of that, it's been the battery that's really let electric cars take off, electric planes take off, all of your drones and things like that are electrically powered, has really been because we came up with a very light and high current, high power capability battery. And these are these lithium polymer batteries. Okay, but the challenge of any battery is always to get the maximum amount of energy stored in the smallest amount of space, and to make it weigh as little as possible. So that's always the challenge for any battery. So here we see the schematic symbols for a battery. Now both of these are acceptable symbols for a battery. This is the one that's indicating it's a single cell battery, and this is the one that's indicating it's a multi-cell. But believe me, you don't need to look specifically as to whether a battery has a single or multiple cell in order to know how to represent it as a schematic symbol. Either one of these will do. So you can make your choice at the time you draw your schematic. If you're representing a DC source, even one like in the lab, you represent it like this. This is the schematic symbol for a battery. Notice how, again, the larger plate is the positive, and it's the shorter plate that's the negative every time. So when we say plate, these would be the plates, and this is the shorter plate. Now, what's the result of connecting batteries in series and in parallel? So as far as our course goes, we're going to consider only two electrical connections: the series connection and the parallel connection. Any of the connections that are other than series and parallel, which really there's only one other called the bridge connection, that'll be explored in your Elect 291 course in the next semester. But for this course, you can be guaranteed the only connections we'll be looking at are either series or parallel. So in this example, what we're looking at is a series connection for two batteries or two DC sources. Now when it comes to the series connection, what defines a series connection is there's only one path for current to flow here, right? So if we think of current leaving the positive terminal and coming around in a circuit, let's say, even though this is an open circuit, there's no closed circuit shown here. You can see it's open. Sorry guys. If you were to connect a circuit, the conventional current would be in this direction, but the thing is there'd be only one path for current to flow, and this is what through these sources, and this is what defines these sources as being in series, only one path for current to flow. So when we look at the current that would be conducted by these batteries when a load is connected, you can see with one path for current to flow and a connection that is positive to negative, and if there was more in series, positive to negative, what we have is additive voltage. the pressure is increased. So the pressure is increased from a single battery to that of 2 batteries, to that of 3 batteries, to that of 4 batteries. Each time the voltage is going up by an amount equal to the battery's potential or its voltage. So here we have 2 1.5 volt batteries. So that would be E total would be our E1 plus our E2. And if we think of this as E1 and this is E2, then we could say that's 1.5 volts plus another plus 1.5 volts to give us a total of plus 3 volts. Now, remember, if I use this as plus 3 volts as opposed to just 3 volts, what I'm saying is I've started down here and I've worked my way up such that with respect to this point down here, this is plus 3 volts. Otherwise, just saying that that's 3 volts as a total amount of charge separation between these two terminals as just 3 volts is perfectly correct. The plus 3 volts is indicating that you took this negative terminal down here as a reference and you added the voltages up such that they were all positive with respect to that point to give you plus 3 volts. Okay, so whenever you want to create a battery bank, and so this is called a battery bank when you take a single battery and connect it with others to create a battery bank. This battery bank was a series connected battery bank where I used the series connection to increase the voltage value. Now if we think about current in this case, the current would all be the same. So that's one thing we have for a series connection is additive voltage, but current is all the same. So here's where we look at the parallel connection. So this would be called a parallel connection. And this is where we have the batteries connected positive to positive, right? And if we had more batteries connected in parallel, we'd just continue to connect all the positive leads together and then all the negative leads together. And it would be a parallel connection. This is the schematic that you see here for parallel, right? But notice how here there's more than one path for current to flow. There's the path up here through this battery, but there's the path here through this battery. And it's joining at these points here. The current flow is joining at these points. The characteristic for the parallel connection is that now instead of current, voltage is the same as just 1. The voltage is the same as just 1. Currents add. So if we've got a 1.5 volt battery and we put it in parallel with another 1.5 volt, our total voltage is going to be 1.5 volts, but our total current will be battery A's current. So I total for the total current will be I battery 1, IA, plus the second battery, IB. So I total will equal IA plus IB. If this is IA and this is IB, the total that you would find here when you connected a circuit would be I total equals IA plus IB. Hi everyone, I thought I'd just take a minute here to show you in reality voltage sources connected in series to give you a greater voltage, but to have the same current that's available from just one battery would be the same when you have them connected in series, because there's only one path for current flow. So if we take a closer look at these batteries here,
in my RV here, I've got two 6-volt batteries to power up a 12-volt system. If you look closer, look at this wire here that's connecting the two batteries together. Notice how it's going from the positive terminal to the negative terminal here to give you that series connection. And the 12-volt connections are across the two series connected batteries here. Okay, so if you look over here, you can see the negative for the system and the positive for the system. And there's a few wires that run a few different systems here, but they're all 12-volt systems. So what we're going to do is we're going to use the voltmeter here just to demonstrate the individual cell or the individual battery voltage, and then how the series connection is adding the two voltages together to give you the total battery bank voltage. So this would be considered a two bank battery bank with two batteries. So I'll just show you that here, and we'll look first of all at the first voltage of the first battery. And if we look at the meter there, we can see that battery 1 is I'm just not getting a good connection. Battery 1 is 6.84 volts. Okay, and now I'm going to take a voltage reading on the second battery, and you can see it's 6.84 volts, so that's two batteries at 6.84 volts. And then I'll show you the combined voltage of the two at 13.68. So you know, if you add 6.84 to 6.84, you get 13.68 volts, and that's the combined voltage of the two batteries connected in series. So other DC voltage sources are electronic DC power supplies, which this is what we have in the lab. So in K012, that's what you were looking at and reading voltage with your voltmeter the other day. Again, solar cell, a solar panel gives you DC output. So whenever we are looking at using solar panels to give us power for AC devices, it has to include something called an inverter to change the solar panel's DC voltage to an AC voltage for us to power our normal household loads. So we have solar cells and then DC generators. Now a DC generator is actually a rotating machine with mechanical input. So it's mechanical input, so like a gas engine or something like that, a mechanical input, and DC electric output. Now this is opposite to something called an alternator, which is mechanical input again, but an alternator gives you AC electric output. So when you have mechanical input and DC electric input or output, this is called a DC generator. Okay. Okay, so this is like what we covered in the lab, and that is that we used a voltmeter. This is the DMM, or digital multimeter. Over here, this is an example of an analog meter. Now remember, I talked about the LFR rule in lab, and what did that mean? That meant you had to first of all look at the leads when using a meter and make sure you put them in the right spot. So when we look at these two examples of meters, notice how this one here, just like what we saw in the lab, is indicating for voltage. One of our test leads would go here, and then of course we'd have our common lead in there that never moves. But if we're using the LFR rule and going to measure voltage, obviously we got to make sure our leads are in the right spot. Now further to that, then we go down to our function. So the function dial is found right here in the middle of this meter, and notice how if you look closer you can see that this has been set to function as DC volts. We see the V and the line like this that indicates that that's DC.
DC volts. And we saw what would happen if you tried to read AC volts from a DC source. You'd get 0 when there's actually voltage there. So it says we're going to measure voltage by placing our voltmeter leads across the component. So this is a common term used in voltage, is to say the voltage across the supply or the voltage across the load is always on either side of the load. Where you're going to see the pressure difference is on either side of a load or either side of a source. The red lead is the positive lead, the black lead is the negative leads, and if the leads are reversed, you get the opposite polarity. When it comes to this analog over here, you'd still apply the LFR rule, and this is where it would make it a lot more important to make sure you're taking into account the range part of the LFR rule, because over here, if you don't have the right range setting set by this knob here, you could actually damage the meter movement by having it move so quickly and so violently that it damages this part of the meter right in here where you find the meter movement, it's called. Okay, so how to measure voltage then? Voltage is measured across. So here we're measuring across a DC source or a battery. Notice how we've set the function switch to measure DC volts, right? So that was important, DC volts. Here for this connection, we put the black lead on the negative side of the connection and the red lead on the positive side of the connection. And so therefore our display would be measuring the total amount of difference, but it would also indicate that the red lead is connected to a more positive point than the black lead. Okay? So what if we look down here? Well, we could say that we have a source voltage here coming from this battery or this DC source with a positive and negative polarity. So if we follow that around, we would see that would give us a positive and negative polarity from this resistance and a positive and negative polarity from this lamp. And therefore, we would have the red connected to the most positive potential and the black connected to the most negative potential. This would be representing a plus 70.3 volts. And again, we have the selector on DC volts because we have a DC source. Okay, this is what's called an across connection. How to measure current. The current you wish to measure must pass through the meter. So remember we talked about current being a single point measurement. This is the way we make the ammeter a single point. It means that we have a point right here when the current flows through the meter, of which the volume of electrons that passes that point is essentially being evaluated per unit time and then displaying a value in amps or coulombs per second. Now, if we're going to have a meter, like an ammeter, become a single point within a circuit, that means we have to break the circuit or open the circuit and insert the ammeter as a point of measurement. So that's the difference between an ammeter, is we have to break the circuit and connect it in series with the loop, whereas with a voltmeter we can just connect in parallel or across all of the devices to measure voltage. But when it comes to an ammeter, we have to open the circuit first and then insert the ammeter. It's a two-step process. So notice how here, if we go with the LFR rule again, we had to have our leads in the proper position to measure current, and we had to set our function switch to measure DC amps. And then of course here we've got current. Remember, conventional current flow is into the positive here, going positive through to negative, and this is the direction of current that's going to result in a plus value for a current. Now remember, when it comes to current, there is no polarity for current. When it comes to voltage, we can definitely say that the positive lead is going to give you a more positive charge than the negative, and vice versa. And so we can assign plus and minus to our charges. When it comes to plus and minus for current, we're just simply saying that if we're going to, simply just indicating direction. So if it shows a plus, then it's our conventional plus to minus direction for current. If the meter shows a plus, if the meter shows a minus, it means you've connected it such that you have current going in here and coming out there. In here and out here would result in a negative value for current. That would make that negative. Okay? It's simply just indicating the direction of current through the meter. Okay, so how would we measure the current in this loop? Well, we know it's indicating we have 16.7 milliamps, but how would we actually measure that with an ammeter? Well, the thing we need to understand is this loop has to be broken. So that means we have to open this circuit by disconnecting it somewhere in this loop in order to put the ammeter in series. So here's where we did exactly that. See how we opened the circuit, inserted the ammeter, made the ammeter a single point. So we now made this ammeter a single point within that circuit so that it could measure the flow of charge through it. And you can kind of think of it just like a flow meter for water, the same one that's used to charge you for how much water you use from the city of Calgary. This is the same idea. It's a flow meter. It's indicating how much flow is passing through that meter and therefore how much is flowing in that circuit. And notice how you've got current entering the plus and exiting the negative. So the current is going in here and coming out there. That's consistent with conventional current flow. So this is going to be a plus polarity showing there. Not because it has polarity, but simply indicating the direction. Okay, so let's just take a quick review of what we see here. Based on what you see for a connection, would you say that this meter measuring this lamp, is it measuring the lamp's voltage or the current? Well, we can see that in this case, this is what's called an across connection. This is a 2-point measurement. It's point A and point B. A 2-point measurement across a component would be obviously voltage. So this is a voltmeter. Whoops, voltmeter. Over here, notice this is a single point, and this has been added in the loop as a single point measurement. This has got to be measuring current, so this is an ammeter. And we can tell that simply by the way it's connected in the circuit. Okay everyone, just picking up where we left off here. We left off at this slide talking about switches. So when it comes to the switches that we see here, we're talking about acronyms to describe each one of these examples. And the first thing to understand is when you're talking about a pole of a switch, you can think of it as the pivot point of a switch. So if we think of this first one as a single pole, single throw switch, its schematic symbol looks like this. It's got a single pivot point and a single throw. So it has a single contact and again a single pivot point back at this point here. This is what would be called the pole. So the schematic, the symbol I've shown for this first one is a single pole, single throw, and the acronym for the first one is SPST, single pole, single throw. If we look at the second one, remember it's a single pivot point, but it has double throw. It has a double throw. So the schematic would look like that, and following the same acronym, it would be single pole, double throw. Next one, of course, is double pole single throw, so it would be double pole with a single throw. That's where you can simultaneously operate two switches, or you can switch two circuits with a single throw of a switch. And so in this case you tend to see a dotted line here. So just let me show that again. A dotted line indicating mechanical interlock between those two throws. So this would be a single pole single throw. Now, one thing we haven't included here, I'll just tell you, would be a double with mechanical interlock in there. That would be called a double pole double throw, DPDT. Okay, push buttons then look like this. This would be a normally open push button, such that when you push on the button it becomes closed. So this would be normally open push button. And here would represent a normally closed push button. The normal state is the way the schematic shows the switch, and so here, pushing down, it would go from a close to an open. On the top, this one would go from an open to a close. So that's our push buttons. Here we see a single pole single throw switch. When it's in its open state, it's like that valve in that water circuit. It's turned off, so there's no flow. So in this first example, there would be no flow. And because there's no flow, you can see the lamp is not doing any work, because remember, it's dependent on flow to do work. And so it's in the off state. You would still have a voltage being read here of voltage equals source. But over here, no doubt the voltage would equal 0 volts. Because remember, you need flow to develop that pressure difference, or that potential difference, or that voltage. Here now that we have the switch closed, now this is a closed switch, right? It's in its on state. It allows flow. It means work is, you've enabled the load, and there'll be work done by the load. So with a voltmeter over here, this voltage will equal V source. It'll equal the same voltage as the source. And that's because the difference of potential that's caused by the current flow here will equal the source voltage. So this is an open switch, or what would be called off. And this is an on switch, which allows current flow and enables the load. And that's using a single pole single throw switch, which we know is SPST. Single pole double throw. This is an example of one of your three-way switches that would be in your home. So in order to make some sense of this, let's say this is at the top of the stairs. This is at the bottom of the stairs. And let's say this is a stairway light. Okay, so the idea being with this wiring of these two single pole double throw switches, that if you were to be at the top of the stairs and turn on the light to see your way down, when you got to the bottom, you could turn it off without having to go back up. And so this is called a three-way switch. So imagine this as you see it right now with the two switches in their on state. You can see there's a path for current flow, and you know the load, being the lamp in this case, is dependent on current flow to do work. So provided there's current flow, the lamp is going to be on and doing work. But now you're at the top of the stairs, and you've worked your way down and you're at the bottom now and want to turn it off. It just means that you're transitioning this switch into an off state and opening the circuit. And if you did, then what you'd end up having is a closure here now, but you've broken the path to complete the loop. So what does that mean if somebody comes to the top of the stairs now? Can they turn on the light again to come down the stairs with the light on? Well, yes, at the top of the stairs, all they do is move this switch to this location, and now the drawings get a little bit messy, but now you can see that through both of these switches, this one in its current state that I've shown and this one in its current state, there's now a path for current to flow again, and the stairway lamp would be on, giving you light until you got to the bottom. And then of course what would happen when you got to the bottom of the stairs? The switch would go back into this state where it was, and you'd break the circuit again. So that's an application of a single pole, single throw. And in your house, this, instead of being called an SPDT, is called a three-way switch. Okay. So next thing we're going to talk about is fuses and circuit breakers. Fuses and circuit breakers are there to protect all the components that make up an electric circuit. And what we need to realize is when we're talking about components in the electrical circuit, it's not just the load, it's all the components. So all of the components that make up an electric circuit are the source, the wires or the conductors, and the load. So we want to have overload protection to protect the source from overload conditions, the wires from overload conditions, and the load from overload conditions. So overload protection, it's called, comes in the form of fuses and circuit breakers. So they're protecting all the equipment from overpower situations or overcurrent situations. So fuses need to be replaced, and you probably are aware of a fuse in your car or something like that, that if you have a fault in that circuit, it'll blow the fuse and you can't reset it, it has to be replaced. So fuses are metallic elements which melt when they see overload, and you can't reset them, they have to be replaced. They come in both slow blow and fast blow. Slow blow fuses are used for circuits where there's a little bit of initial surge current that's above normal load current that needs to be allowed when it's first turned on, and then if it sees a sustained excess of current, it'll blow, and that's what's called a slow blow. It protects against false trips when you have an inrush current. And then fast blow is just as soon as it sees the current in excess of its rating, it'll trip or it'll blow. So when current exceeds the rated value on a circuit breaker, the magnetic field produced by the excessive current operates a mechanism that trips open the switch. So that's what we have when we have a circuit breaker. Now a circuit breaker can be reset once the fault condition is removed. So this is what the schematic symbol for a fuse looks like when you put it in your schematic. And then down here, if we look at the examples that are in this picture down here, these are all fuses. So these are fuses here, and of course they have to be replaced once they're blown. These two here are examples of circuit breakers, right? So this is one for a 120 volt circuit. This is one for a 240 volt circuit. That's how come it's wider. It incorporates two legs of the connection as opposed to just one in neutral. So that's 120, and this is 240. So you will see some other examples of schematic symbols showing that for a fuse. Not very often. Most often it's this as you're representing your fuse, and then breakers can be shown like this, right? And you'll probably, I would say, primarily see a breaker like this shown in our curriculum and stuff. Whoops. Okay, so that's the end of that slide presentation, guys. I'm just going to do a couple of little videos showing some meters and switches and batteries connected in series, just to give you a better idea in reality what some of this looks like that we've looked at by diagram. Okay, so I'll publish this on D2L and work on those other videos. Hey there, so remember I talked about just going to show you switches with an ohm meter inside. And so notice how we've got a couple of switches here that are on or off switches. We know they are actually single pole, single throw switches because there's only two terminals on each switch. If they were single pole, double throw, there'd be 3 terminals. But knowing there's only 2 terminals, we know they're single pole, single throw switches. What we're going to do is take a look at their on-off conditions in terms of resistance using an ohm meter. So I've got this meter set up as an ohm meter. Remember, you can follow the LFR rule there. We have the leads in the right place for an ohm meter. We have the function switch set for ohm meter, and of course it's an auto ranging meter, so we're okay on the range part of it. Now, if I'm going to look at resistance for any component, I've got to make sure that the component is not powered up or not connected to any circuit. So you can see here we're not connected to any wires or any source of voltage, and so we're safe to be doing a resistance measurement. So I'm just going to take this switch here on the right, and I'm going to first start with it in the off state. You can see it's clearly in the off state. And then I'm going to go to the 2 terminals of the of that switch and measure the resistance. And if you look at the ohm meter right now, you can see it's measuring OL. And from the lab, we know that means that it's reading greater than what that ohm meter can read. And that ohm meter can read up to 10 mega ohms or 10 million ohms. So what it's saying is we have an open circuit value. So we have 0 current flow for open circuit value because the switch is in its off state. Okay, now we're going to change the switch to on, and in changing the switch to on, we should now have a short circuit and 0 ohms of resistance because this is going to allow current flow. So this is going to enable current flow in a circuit and allow the load to do work. So I'm just going to connect to the leads here with the ohm meter, and then you can see I've got 0.2 ohms, which is short circuit equivalent for a switch that's in its on state. So that's one way we can always check switches to see if they're working properly. When we have a switch that's on, it should be a short, and when it's off, it should be an open. One of them allowing current flow and to enable a load to do work like a light or a motor or anything like that, or a heater. Or to disable current by providing an open circuit in the off state and turning the device off. So that's it, guys, and I hope you find that helpful.